Okay, so in the last class we were discussing about the oscillators, and we have seen RC phase shift oscillator as well. So when we are going to discuss about the phase shift oscillator, so we have also seen that the frequency of oscillation, so that is going to be produced by this one RC phase shift oscillator will be limited to only up to 100 of kilohertz, 100 less than 100 kilohertz, and we have seen the expressions by drawing its corresponding AC equivalent circuit, and we have seen the current that is flowing in each of the RC section, and we also know that 180 degree phase shift is going to provide by the transistor itself. Another 180 degree is going to be provided by this RC network. So total 180 total 360 degree phase shift was there. And we have seen that in order to find out the loop gain, so we are going to write down the corresponding current equation in the feedback, and we are going to see what will be the feedback voltage with respect to input voltage. So if you know what is the gain with respect to output to input, it means that from the feedback signal to the input signal, if we compute, so if you have to, it has to be um, it has to be greater than the feedback gain. So the gain obtained by the amplifier along with the feedback is going to it must be equal to 1. So A into beta. So A corresponds to the amplifier gain, and B corresponds to the beta corresponds to the feedback. So whenever you're going to have a loop gain, whenever you're going to have a loop gain is equal to 1, whenever you're going to have a loop gain is equal to 1, so you're going to get a sustained oscillation. So in order to get that sustained oscillation, you're going to find out what is the feedback voltage, and we have seen that so feedback voltage is the input signal voltage. Okay, so kindly mute yourself, all of you. Okay. So in order to find out, so we have found out the expression which was having real part as well as imaginary part. So when we are going to solve this one, so where alpha corresponds to 1 by omega RC, and we can say that alpha as alpha is given by a constant term which is denoted as 1 by omega RC. So if you substitute over here, so you'll be having this as a real part, and the imaginary part also will be there. So in order to get the how much will be the frequency of oscillation provided by this RC phase shift oscillator, then we'll be knowing that by equating into the imaginary part. Okay. So by equating this to the imaginary part, so we will get the frequency of oscillation. So here we can see omega square, alpha square will be equal to what? So this will be the alpha square. So alpha square will be equal to 6. Okay. So when you equate the value of so omega square, so you're going to get the frequency of oscillation for as this. At the same time, if you're going to equate the real part, so if you are going to equate the real part, so 1 minus 5 alpha square, which will be equated to minus gm into rd dash, then you will be getting the how much should be the gain parameter. So 1 minus 5 alpha square will be equated to minus gm into rd dash. So alpha square, we know that alpha square is given by what? So alpha square is equal to 6. So if I'm going to substitute over here, so alpha square corresponds to what? So 6 into 5, 30. So 30 1 minus 30 means minus 29. So minus 29 minus 29, if you it will get cancelled, and you will be getting gm into rd dash will be equal to 29. So this is how you're going to get the equation for this 29. Okay. So by equating the real part, so you're going to get the what should be the gain parameter, and by equating the real part, you're going to get so how much the gain has been reduced. So the beta, you're going to get the beta is equal to what? So beta will be getting as a 29 over here. So by substituting the value of alpha square is equal to 6 over here. So when I substitute the value of the in the real part will be substituted to find out the gain reduction factor, whereas this imaginary part is going to substitute for the frequency of oscillation. So we have obtained the frequency of oscillation as 1 by 2 pi RC into root 6, whereas when we equate the real part to the gain, so this is the feedback part. So 1 minus 5 alpha square will be equated to minus gm into rd dash. So if I'm going to equate that, so you will be getting the what will be the gain for the feedback network. So substitute the value of alpha square. So alpha square is equal to 6. So if I substitute alpha square is equal to 6 over here, 6 into 5, 30. So 1 minus 30, it is equal to minus 29. So minus 29 will be equated to minus gm into RD dash. So this is what, so amplifier gain, and this is the limit of feedback gain in the real part. So we are going to equate the real part with the amplifier gain parameter, so that you are going to get the expression. So that is the beta, or the gain of the factor is going to reduce by a factor of 29. So this 29 has been obtained by substituting the value of alpha square is equal to 6. Okay. So with this, we are going to obtain the gain of the amplifier should be greater than 29 in order to have a loop gain should be equal to 1. So if it is going to satisfy the amplifier with a transistor or any type of amplifier, if you are going to consider, so if the amplifier gain is greater than 29, then you are going to get the loop gain will be equal to 1. So this loop gain, so gm into RD dash, if it is equal to or greater than 29, then you are going to get the loop gain is equal to 1. So if it is equal to 1, then it is going to satisfy, and the Parkinson filter, and it will circuit will start oscillating, and it is going to produce a sustained oscillation, sinusoidal oscillation. So by itself, without any external trigger pulse, so by with the help of a positive feedback only, so it is going to get triggering by once it gets triggered, so it will provide a sustained oscillation as long as the power supply is on. So you can see here is only the power supply which is being connected, so it is VDD. So if as long as the power supply is on, you are going to get the sustained oscillation through the implementation of the this feedback. So in any type of oscillators and all, if you consider, so oscillators you are going to have oscillators will be having employing a positive feedback. So you here you're going to get a sustained oscillation, and once triggering of the pulse is required, so it is going to get the waveforms will be getting by its own, and it is going to provide. So oscillators, so when we look into the circuit, so in the next chapter we are going to start in the next class. So when we are going to start the next topic, I am going to explain so feedback and what are the different types of feedback in that feedback. So these oscillators are some of the examples which is going to be taken for the positive feedback. So in that positive feedback, we are going to take it as oscillators as example, because it is going to provide a sustained oscillation, as well as the waveforms are the what we say, the output is going to be exponentially increasing in the case of positive feedback. So the same thing we can but in the case of negative feedback, we will be not getting the gain, that is the gain is not going to be the gain is going to be in control form, whereas not in the case of positive feedback. So this schematic trigger circuit, triple pi timer, all these some of the examples of the circuits are there, so which are going to work with respect to positive feedback. So here this oscillators is also example, so which is going to imply positive feedback. So because of this positive feedback, you are going to get sustained oscillation. So after understanding the RC phase shift oscillator, and we have obtained the loop gain should be equal to greater than 29. So we have moved to the next class of the topic, which is nothing but LC as well as a crystal oscillator. So when we are going to have a crystal type of oscillators, LC as well as a crystal oscillator, so we are going to have an inductor as well as a capacitor circuit will be there. So in this inductor and the capacitor will be inductor as well as a capacitor in the feedback path. So whenever we are going to have inductor as well as a capacitor in the feedback path for the normal amplifier circuit, so if you are going to have a feedback element as the inductor as well as a capacitor, so you are going to we are going to have a we will be calling it as a LC tuned circuit, and since you are going to have a feedback path as a L and C, so you can see these two both are considered as a energy storage device, and because it is going to each one of it is going to store in the respective form in the electrostatic as well as in the magnetic field. So we can say that since it is going to have a feedback path as an energy storage element, so it is also called as a tank circuit. So tank in the sense it is going to store the energy. So the NR is going to have a feedback as an inductor as well as a capacitor. So you are going to call it as a tank circuit, and at the same time, whenever they are having inductor as well as capacitors, there will be always certain amount of losses is going to be exhibited. So either in both capacitor as well as inductor. So there will be some leakage loss in this one, as well as there will be some current loss in this circuit in the inductor. So in order to overcome that, so we are going to employ one resistance R, which is going to connect between them collector and the emitter. So which is going to provide a constant amount of current that is going to supply. So in order to overcome this losses that are going to occur between the capacitors and the inductor. So this is about the circuit. So this is an amplifier circuits, and this is the feedback element which has been employed. So since the output to the input has been employed, so there can be output two types. So the LC tuned circuit can be considered into two categories broadly. So one is by using feedback elements. So whenever you're going to use LC tuned circuit, so you're going to have three impedance going to be connected over there. So one is Z1, Z2 as well as Z3. So Z1 and Z2 will be always made up of same type of elements, and the Z3 will be opposite elements. So it can be L and C. So here in this case, it has been considered as the Colpitt oscillator. You have to remember that Colpitt oscillator Z1, Z2 is made up of same element, that is a capacitor, and the Z3 is made up of Z3 is made up of inductor type. So this type of oscillator in which you are going to have a capacitor getting divided. So here C1 and C2 will be having the common type, which is nothing but capacitor divider circuit, and inductor will be there. And also in the another type of form of a LC tuned circuit, wherein which you can employ a feedback with inductor and capacitor as a inductor divider. So here you can see Z1 and Z2 is made up of inductor, and Z3 is made up of the capacitor. So since we are going to have this type, so it is called as inductor divider, and this type of oscillator will be called as a Hartley oscillator, and this type of oscillator is called as a Colpitt oscillator. So Colpitt oscillator, so there will be capacitor divided, so two capacitors will be there on the feedback path, and one inductor will be there. So whereas in the case of Hartley oscillator, so we are having two inductor along with the capacitor. So that's what about the the Hartley as well as the Colpitt oscillator. So next is how we are going to get the frequency of oscillation. So in order to get the frequency of oscillation, so the main thing you're going to get is so when you're going to have this Hartley or Colpitt oscillator, so the frequency of oscillation, so which is going to be provided by this will be usually in terms of greater than 100 kilohertz to 100 kilohertz to a few hundreds of megahertz. So the frequency, whenever the crystal frequency or the frequency of oscillations are required is more, so that means the higher frequency of oscillations is required, we are going for LC circuit, or that is a LC circuit or the crystal oscillator circuit. So wherein which it is going to provide a higher frequency of oscillation. Along with that, the oscillations are all stable when compared to that of RC phase shift oscillator. So there it is known to have lesser Q factor, that is the quality factor, so which is very important in the oscillators. So higher the value of Q, higher will be the stability as well as the sustained oscillations it is going to be. So the value of the higher because of higher Q, so you're going to have we are going for LC as well as Hartley as well as a Colpitt oscillator. So we are going to see what is the frequency of oscillation. So for the Colpitt oscillator, so the frequency of oscillation which we are going to get is given by 1 by square root of L into C. So C can be equivalent capacitor. So C in this oscillator, Colpitt oscillator. So L into C1 C2 divided by C1 plus C2. So that is the frequency of oscillation that is going to get for the Colpitt oscillator. So omega naught is nothing but the frequency of oscillation for this Colpitt oscillator will be given by omega naught is equal to 1 by square root of L into C1 C2 divided by C1 plus C2. And in the case of Hartley oscillators, the frequency of oscillations you are going to get as omega naught will be equal to 1 by square root of L1 plus L2 into C. So that is what frequency of oscillation. So in both of the circuits, so the frequency of operation also it is going to be happening for a higher frequency of operation, because at lower frequency you can see, So when whatever the capacitor is there, so at low frequency, if it is going to operate, means these two capacitors, it will be acting like the open circuit. It is not going to provide any energy. So storage, because it is going to have a high capacitive reactance when the frequency of operation is lower. So we're going to operate the frequency of operation if it is low. So if the frequency of operation is sufficiently low, that means the transistor capacitance as well as the frequency of the resonance parallel tuned circuit will be having only the feedback path as a inductor. So when it is going to have, so capacitors will be can be neglected. So capacitors can be neglected when if the operation of the frequency is lower. So at the same time, so we are going to see what is the loop gain. So in order to find out the loop gain, so we are going to write down the corresponding circuit. So Colpitt oscillators we are going to see in detail. So the Colpitt oscillators, in this Colpitt oscillator we are going to explain in detail. So in this Colpitt oscillator, so we are going to see, so the ratio of the feedback factor. So the feedback factor is plays a very major role. So same like so how we are going to get in the Okay, so it was there internet up. So just because the Wi-Fi connection was there, power went off. So I could not. Because of that, it has been exited. So I'm just connecting through mobile. Well, also your network will be good. Okay, just confirm. All of you, whether my voice is audible?
Yes, sir. Audible, sir.
Okay, you can see where I was discussing about LC tuned oscillator, right? So this omega naught, so this is the frequency of operation, and now the ratio. So we know that in order to get the loop gain to be equal to one, so you're going to have a ratio for the oscillator. So you should have we are going to write down the corresponding circuit. So over here, so the equivalent circuit of the Colpitt oscillator, you are going to maintain like this, and oscillator circuit, equivalent circuit has been written over here. So in which you can say, so this is a transistor. It has been replaced by its corresponding voltage. Whether my voice is audible?
Yes, sir. Audible, sir.
Okay. That's what I was displaying. So in this NC crystal oscillator, so we are going to replace the entire thing, and we are going to okay. So the circuit transistor has been replaced with its corresponding equivalent circuit, and remaining thing as it is the feedback is being considered. So we are going to have C1 and C2. This is the in the feedback part. So it is the good Colpitt Oscillator in which C1 and C2 capacitors will be there. And correspondingly, so we are going to neglect corresponding small signal equivalent circuit we have written for the transistor BJT. So here, since we are going to use the BJT as a transistor over here, so corresponding small signal equivalent circuit, voltage controlled BJT, we are going to represent in terms of voltage, wherein which you are going to see that a small resistance which is going to connect between the base and emitter has been removed. So in order to simplify the purpose, so we are going to have only the voltage has been written. So since it is very small resistance is associated between this one, along with that capacitance which is going to connect between the base and the collector. So that is C mu. So C mu as well as the R pi. So we know that this is a pi model. So we'll be having resistance, that is small resistance as well between base and emitter, and at the same time, so capacitance, a small capacitance which is going to be there between the base and between the base and the collector. So it will be same. So that is mu. C mu will be there. So that is going to be absent in order to simplify the analysis purpose. So we are going to have that one C mu. So that is the C mu capacitance will also be neglected, and we know that the voltage across the base to emitter, so it is nothing but term, so the V pi, so that is a base to emitter voltage V pi is there. So this V pi is going to control the current that is going to flow between the collector to emitter, that is the collector current, that is the GM into V pi. So this is nothing but term collector current itself, so that is going to be represented as a GM into V pi, and we are going to we are going to find the analysis of the voltage that is coming. So this is the input voltage that is going to be applied over here across the base and diameter, and across the collector we are going to have we are going to have return voltage. So because the return voltage is nothing but a feedback voltage, so if you are going to get the feedback voltage, then only you can able to find out the loop Sorry, here some internet issue is there. So because of that, it is the call is dropping. Okay, whether my voice is audible now. So whether my voice is audible.
Yes, sir. Audible, sir.
Okay, so you can see this is the circuit. So now writing down the node equation across the collector node. So we are going to see what is the voltage, because if we know this voltage across this one is nothing but input voltage, and the voltage across the collector is nothing but feedback voltage. So when you take the ratio of the feedback voltage to the input voltage, then you will be getting the loop gain. So in that order we are going to see this will be the return voltage that will be connected back to the input side. So if we know what is the voltage across this collector node, so that is by applying the node current equation. So you're going to see, so what is the voltage. So we are going to find out at node equation at the across the collector node C. So we are going to find out write on the expression. So what is the voltage? So we will be seeing that this is the gm into v pi is the current source, and for which across this collector, so you will be having the same voltage, so that will be proportional to that of the input voltage. So this is the voltage across the input side, and the same proportional voltage across the output, along with the multiplication with the multiplied with the factor of transconductance over here. So here also it will be having the same voltage will be developed across here, so that is equal to v pi. So 1 plus r into c1 into v pi it will be having. Along with that, here you will be having the capacitor capacitance 2 as well as capacitor 1, both will be having the voltage drop across C2 will be having the same, since the voltage across C2 will be directly connected to that of this one. So you're going to have see what is the voltage across here. C2 will be equal to S into C2 into V pi. So this is the capacitor which is going to fed back to the input. So at the same time, what will be the effect of the voltage across here? So this will be we are going to find out. So across this node C, collector node C. So you're going to see that these C2 is also going to be part of this feedback part. So you're going to have the expression for node voltage VC across this one will be because of C2 as well as L as v pi into 1 plus s square into 1 plus s square into L into C2. So this is the voltage that is going to be multiplied along with the this voltage across this component R lower R plus C1. So in this way, so you are going to find out the voltage across this. So this is the voltage VC that is going to have this feedback path multiply with this part, so that is going to have the total voltage across node C. So if we find out this node voltage across C, and we know this voltage across input voltage to the base emitter, so that we can able to find out the voltage gain. So S into C2 into V pi. So here whatever the voltage across this time is S into C2 into V pi, and the remaining things. So because of this is also a part of the capacitors in the feedback part. So we are going to have see the voltage across here. So that is V pi. So that is the voltage across this node is V pi into, so 1 plus s square. So s square is nothing but because L and C both are component are there. So s into L and s into 1 over C 1 over s into C2. So it is going to have s square into L into C2 into V pi. So along with that, across this part, because of this component resistance and capacitance 1 over R plus C into C1 into V pi. So that you are going to see over here. So I have just written the node equation across the collector terminal. So this will be equal to 0. So this is equal to 0. So and also we know that the input voltage V pi cannot be equal to 0. In order to provide any oscillations, the voltage across the input must be there. So we are going to see that V pi will be not equal to 0. So since V pi, if it is equal to 0, then you will be not getting any oscillation. So if V pi is if it is equal to 0, you will be not getting oscillation. So V pi cannot be equated. So V pi cannot be equal to 0, and also we can substitute this expression. So entire expression. So entire expression I can entire expression. So I can write it in apart from the V pi. So I'm going to equate to 0, and you're going to see it's a 1 by 1 equation. So s term is there, s square term is there, s cube also it will be there. So if you see this is a s term, and here also s term is there. So whenever it is multiplied with this one, so you're going to get s square term. So s term, s square as well as s cube, so you're going to find out term. So each of the term, so that is in terms of physical frequency, that is a complex frequency variable you're going to have. So if I substitute the value, so simplify this expression, you will be getting the equation. So that is going to have higher cube, that is um, s power 3 s square s, and remaining that will be equal to constant. So all these things, if we simplify again to have a real part as well as imaginary part, so by substituting s is equal to j omega, so when I substitute s is equal to j omega in all these things, so you can say that s cube means you will be having odd term, whereas s square means you will be having even term. So even term means j square will be equal to minus 1. So j cube means minus 1 into j. So you will be having again, you will be having the imaginary term in the odd roots. So you will be having this one as well as s term as well as s cube will be having odd root, and remaining s square and constant term will be having the real part. So that gm plus 1 by r will be having the real part, and s square, s is equal to j square is equal to minus 1. So I'm going to have this term will be real part, and these two terms will be categorized into imaginary part. So as in the previous, we have going to get real part as well as imaginary part. So imaginary part will be useful for finding the frequency of oscillation. So equate this imaginary part to 0. So you're going to get the frequency of oscillation for the Colpitt oscillator, as we have seen in the previous. So omega naught. So that is the frequency of oscillation. So that you're going to get for the Colpitt oscillator. And if we equate this real part to the gain parameter, so what is the gain? So that is nothing but amplifier gain, which is nothing but transistor. So transistor will be having what? So it is going to have gm into r. So that is the gain of the gain of the transistor. So if we equate the real part to the gain, so you're going to get the ratio. So that is nothing but a feedback factor. So C2 by C1 will be equated to gm into r. So gm into r corresponds to the gain of the transistor. And if I substitute this entire thing, so you're going to get C2 by C1. So that C2 by C1 is the limit of feedback factor. So that feedback factor, if I'm substituting, so if I am going to get the amplifier gain, so you'll be getting the ratio of feedback voltage to the gain. So you're going to get them loop gain should be, in order to get the loop gain to be equal to 1, so you're going to get them maintain this entire left hand real part. I'm going to equate to the voltage gain. So if I equate, then I'm going to get some equations which is going to provide that loop gain. This is nothing but a beta feedback gain. So this feedback gain, it will represent how much the voltage drop it has been happened because from the output of the amplifier to the input to the amplifier. So that shows the reduction, gain reduction, how it has happened. So that equation, if we simplify, so by equating this to the gm into r, so you will be getting this ratio c2 by c1, that is nothing but frequency. So this is nothing but feedback factor C2 by C1 must be equal to Gm into R, since it is a Colpitt oscillator. C2 by C1. So the feedback factor, so C2 should be equal to Gm into R times of C1. So that is nothing but feedback factor for this Colpitt oscillator. So this is how you're going to obtain the frequency of oscillation for the Colpitt oscillator. And what should be the feedback factor? That means in order to get the loop gain, so what should be the feedback factor? So because of the Colpitt plays a major role in the Colpitt oscillator, capacitor plays a major role. So the ratio of C2 by C1 must be equated to the gain, so that you're going to get the ratio loop gain will be equal to 1. So C2 by C1. So there is no physical derivation will be there. So you have to remember. So the feedback factor C2 by C1 or L1 by L2. So in the case of a Hartley oscillator, the ratio of L1 by L2, that must be equal to Gm times of R in the Hartley oscillator. In the case of Colpitt oscillator, the ratio of C2 by C1, that is nothing but the feedback factor. So that should be equated to Gm into R. So that gives the loop gain to be equal to 1, and the frequency of oscillation with 1. So you need to find out the voltage across the collector. So if I want to find the voltage across the collector, that gives the feedback voltage. And with respect to input voltage, if I am going to substitute, then you will going to get the frequency of oscillation. So by equating the imaginary part of this equation, so we are going to get the frequency of oscillation. And if you're going to equate the real part, so you're going to get the expression for the you're going to get the expression for the loop gain. So the loop gain not to be equal to 1. So C2 by C1 must be equal to Gm into R. So if it is satisfied, then we are going to get the sustained oscillation. So this is about the Colpitt oscillator. With this, I'll just finish off this topic, and from tomorrow onwards, I'll be starting with the module 3. So this one topic is there, crystal oscillator. I'm just seeing. So if it is possible, Monday I will just finish the second module. Okay. Okay, I'll just conclude today's class. Any doubt is there with respect to this topic? So even I'm planning to conduct one quiz. So how other subjects quiz has been done?
They gave a quiz in MS Teams, sir, of 5 to 10
MS
questions.
5 to 10 question ಅಷ್ಟೇನಾ?
ಹೌದು ಸರ್, ಅದಕ್ಕಿಂತ ಜಾಸ್ತಿ ಇಲ್ಲ, 5 to 10 questions.
See that ಯಾವುದೋ Kahoot app ಅಲ್ಲಿ they have not played ಅಂದ್ರೆ like an online game they have not conducted. So who will be the topper? Yaar first, yaar second, yaar third, ಆತರ it will be online. You can play by using Kahoot app. As the principal sir was discussing in the yesterday class. So we have to make this quiz. Why we are keeping quiz? Because one day relaxation will be there, and along with that you will enjoy also. While learning, you will be enjoying and that. So MS team alle quiz ಕೊಟ್ಟಿರೋದು ಅಷ್ಟೇನಾ? So they are not done with the Kahoot app. Okay.
Which app, sir?
Kahoot ಅಂತ ಒಂದು ಆ್ಯಪ್ ಇದೆ. ಸೊ ದಟ್ ಈಸ್ ಕ್ವಿಜ್ ಫಾರ್ ಕ್ವಿಜ್ ಓನ್ಲಿ. ಸೊ ದಟ್ ಈಸ್ ಆನ್ಲೈನ್ ಕ್ವಿಜ್ ಪ್ಲಾಟ್ಫಾರ್ಮು. ಸೊ ಅದರಲ್ಲಿ ರಿಜಿಸ್ಟರ್ ಆಗ್ಬಿಟ್ರೆ ಸೊ ಇಟ್ ಈಸ್ ಫ್ರೀನೋ. ಅದು ಲಾಸ್ಟ್ ಇಯರ್ ಎಲ್ಲ ಫ್ರೀ ಇತ್ತು. ಸೊ ಐ ವಿಲ್ ಜಸ್ಟ್ ಲುಕ್ ಓವರ್ ದಟ್. ಸೊ ಇಫ್ ಇಟ್ ಈಸ್ ದೇರ್ ಐ ವಿಲ್ ಡೂ, ಆರ್ ಎಲ್ಸ್ ಐ ವಿಲ್ ಡೂ ಇನ್ ಗೂಗಲ್. ಗೂಗಲ್ ಒಂದು ಗೂಗಲ್ ಫಾರ್ಮ್ ಕ್ರಿಯೇಟ್ ಮಾಡಿಬಿಟ್ಟು ಕ್ವಿಝನ್ನು ರೆಡಿ ಮಾಡ್ತೀನಿ. ಸೊ ಐ ವಿಲ್ ಜಸ್ಟ್ prepare some questions, objective to multiple choice questions I will prepare, and even I will post in MS Team. But you can directly, I will share the link as well. So if you are since all of you are having Gmail account, so you can easily solve the questions, and once you solve, you can also view the score. So I will just make use of that. So after the second second topic, the last module of the second topic, if it gets completed, so after that I will just conduct that quiz. Okay. So that was on thing I
Okay,
was
sir.
not done for you people. Okay, whenever so problem will be okay. Okay, with this I will just conclude today's session. So I will meet you tomorrow. Okay.
Thank you, sir.
Okay. So all of you, ನಾನು ಹೇಳೋದೇನು ಗೊತ್ತಾ, ಸಿ ಎವ್ರಿ ಒನ್ ಕೈಂಡ್ಲಿ interact with faculty. Okay, so interact with faculty in the sense ಯಾರ ಪ್ರಿನ್ಸಿಪಾಲು HOD ಎಲ್ಲ ಇದ್ದಾರೆ ಅಂದರೆ ಮೀಟಿಂಗಲ್ಲಿ. ಸೊ ಇಫ್ ಎನಿ ಒನ್ ಆಸ್ಕ್ ದ ಫ್ಯಾಕಲ್ಟಿ ಟು ಗಿವ್ ದ this one, so don't hesitate, you can give. Even I can understand. So if I tell anything something wrong, feedback and all, so what they will think about us, like that they will be having some mindset, right? So that you should remove. You have to tell your opinion. So when they are asked freely, you should tell yourself. Okay. Okay, Monday or Tuesday I will just conduct quiz for you people. Okay, thank you.
Thank you, sir.
Excuse me, sir.
Thank you, sir.
ಹೇಳಿ
ಸರ್, ಅದು ಇಂಟರ್ನಲ್ಸ್ ಅಲ್ಲಿ ಆಬ್ಸೆಂಟ್ ಅಂತ ಹಾಕಿದ್ದೀರಾ ಸರ್?
ಚೇತನ್
Yes, sir.
ಅದು ಕೆಲವೊಬ್ರದ್ದು ನೀವು ಏನ್ ಮಾಡಿದ್ದೀರಾ, ಸಿ ಹ್ಯಾವ್ ಸೆಂಟ್ ಆನ್ಸರ್ ಸ್ಕ್ರಿಪ್ಟ್ ಟು ಮೈ ಮೇಲ್ ಐಡಿ.
ಆನ್ಸರ್ ಸ್ಕ್ರಿಪ್ಟ್
ಮೇಲ್
ಮೇಲ್
ಐಡಿ
ಐಡಿ ಕಳ್ಸಿದ್ದೀನಿ ಸರ್.
ಕಳಿಸಿದ್ಯಾ?
ಕಳ್ಸಿದ್ದೀನಿ.
ಜಸ್ಟ್ ಚೆಕ್ ನೋಡ್ತೀನಿ ಹಂಗಾದ್ರೆ ನೋಡ್ತೀನಿ ಬಿಡು. ನನ್ನ ಕೆಲವರು ಒಬ್ರದ್ದು ಅಟೆಂಡೆನ್ಸ್ ಶಾರ್ಟೇಜ್ ಇರೋದಕ್ಕೆ, ಸೊ ಚೇತನ್ ಎಸ್ ಲೈಕ್ ದಟ್ ಏನಾರ ಇತ್ತು ಅಂದ್ರೆ ಪ್ರಾಬ್ಲಮ್ ಆಗಿರ್ಬೋದು. ನೋಡ್ತೀನಿ
Okay.
ಕಳ್ಸಿದ್ದು. ಓಕೆ.
Excuse me, sir.
ಹಾಂ ಹೇಳಿ.
Sir, again I have also sent to your mail, sir, my answer
ಅದೇ
script.
ದಟ್ಸ್ ವಾಟ್ ಈವನ್ ಇವಾಗ ಈಗ ನಿನ್ನೆ ತನಕ ಎಲ್ಲ ಕ್ಲಾಸ್ ಟೀಚರಿಂದ ಏನೇನೋ ಕೆಲಸ ಐತ್ರಿ ಮಾಡೋಕ್ಕಾಗಿಲ್ಲ. ಸಂಡೇ ಸರಿ ಮಾಡಿಬಿಟ್ಟು ಮಂಡೇ ನಾನು ನಿಮಗೆ ಹೇಳ್ತೀನಿ. ಓಕೆನಾ?
Yes, sir. Thank you, sir.
ಓಕೆ, ಥ್ಯಾಂಕ್ ಯು.